Okay, so let's look at some examples when we're talking about point estimates. Okay, so we have a study. So in order to look into the number of, there's a proportion of college students who spend more than 3 hours a day on the internet. So based on this paper, 2,998 of the 7,421 students surveyed reported that they use more than 3 hours per day. So we can use this information to help estimate the true proportion that does that. Okay, so how are we going to do that? All right, well, it would make sense, if we are trying to find the true proportion, to use our sample proportion. That just makes sense. If we have a sample, use the proportion of those people who use the internet more, and that would be a way to estimate. Pretty simple. Okay, so the number of successes, the number of people that we're trying to look at here, we have 2,998 out of 7,421. And so if we're trying to use this to help us, 2,998 divided by 7,421, we get 40.4%. That's a pretty good estimator, 40.4%. So that would make sense to use as an estimate. We would use that to help make our distribution and to test different theories and hypotheses based off of that. So, you know, point estimates can be very simple. Just use something logical. In this case, you wouldn't want to use like the standard deviation to estimate the true proportion. That wouldn't make any sense. It would make sense to use a proportion and use the data from the sample for that. Okay, so let's see an example where we might have some different options. Okay, so we have another paper that talks about people who do, the authors distinguish between how much reading, what the reading habits are of students. Sorry. So they had the following observations represent the number of hours spent on academic reading in 1 week by 20 college students. So we have all of these different numbers. We have some low numbers, we have some high numbers, we have everything. So we have this dot plot here. Looking at the data this way, it can help give us an idea of what the shape is. Is it normal? Is it not? This data, it's not particularly normal, I would say. It's at least seemingly symmetric. We kind of have this wide range. The data seems to be spread out generally enough. So we could have very different data points here. Now, 3 different ways to measure the mean. So you don't always necessarily just want to use the true mean. You kind of want to go a little bit more into it and try to figure out, what we could use. So let's look at our data and let's find our means and medians and standard deviations and all this kind of stuff. So what we're going to do is type all this information into our trusty little calculator. So we're going to go into stat edit and we're going to type our stuff in. So we've got 1.7, we've got 3.8, 4.7, 9.6, 11.7, 12.3, another 12.3, 12.4, 12.6, 13.4, 14.1, 14.2, 15.8, 15.9, 18.7, 19.4, 21.2, 21.9, 23.3, and 28.2. So we've got our 20 observations here. So we want to find our means and all this kind of stuff for it. So we're going to go to stat, calculate, and do our one variable statistics. So from here we've got some information that we're going to go ahead and write down. So our mean, okay, is 14.36. So I'm going to write that down. So x bar is 14.36. We can also find, our median. So our median, our calculator will also tell us that. We go down. Our median is going to be 13.75. And one other way that we could look at the mean is if we did maybe a trimmed mean. So, let's say we wanted to do a 10% trim. So a 10% trimmed mean would mean that we're going to take 10% of the data from the top and bottom. Okay, so let's see, if we did a 10% trimmed mean, that of the 20, that means we're taking 2 from the top and bottom. So an easy way to go ahead and figure this out, we're going to be taking out the bottom 2 and the top 2. Okay, and we're just going to be calculating everything with what's left. So if we go back to our calculator, we can figure this out real quick. We go back to Stat, Edit, and we're going to delete the top 2, or excuse me, the lowest 2. Oops. And we're going to delete the top 2. So delete, delete. Okay, so now we're just left with 16 observations. So we didn't take 10% away. We actually ended up taking 20% of our data away, but 10% from top and bottom. So now we go back and we're going to run our one variable statistics again, and we have a mean of 14.38. Okay, so actually very, very similar to what our sample mean was. So we go back and we do, this is 14.38. So all of these different ways to calculate the mean or to estimate the mean are good. They all work. They're all plausible. It's just about picking the right one. And that's going to be based off of when we do the sampling distribution, when we see what the standard deviation of that is going to be. So this data here is just an example that we could use 3 different measures of the mean in order to actually get what we want. Now, last example we're going to talk about a concept that is true, and that is that even though, okay, so like the mean and sample mean and stuff, those things are said to be unbiased statistics. But what about biased statistics? Okay, well, one biased statistic is that our sample standard deviation to try to estimate the standard deviation, the true population one. They are fundamentally different. You wouldn't think that that would be the case, but they are. We use S as a point estimate to try to measure the true standard deviation. We use S as part of our data. Okay, so even though S is biased, we are going to use it. Now, this is something that is very interesting, right? So variance is the same thing as our standard deviation squared, which we use S squared to estimate that. And this is unbiased. This is an unbiased statistic. It does not fundamentally differ the way that we go about this. But, oh, excuse me, this is the other way around. Apologize. Wait, we use S squared. We can use our sample variance to estimate our sample, our population variance. But this is unbiased. Now, it does not follow. This is a biased statistic, but we use it, okay? We use this over here. We use S to estimate our standard deviation, even though it is biased. And you'll see that when we run this data on our calculator, which I'm going to show you. So we're going to type this data into our calculator. This is about the airborne times for nonstop flights from San Francisco to Washington. And so we are going to go up. Now, if you need to clear a label, you go up to where it says L1. Do not hit delete. You hit clear. Okay? And then we're going to type these in. So we get 270, 256, 267, 285, 274, 275, and I'm blocking some of this stuff. 266, 258, 271, and 281. So when I go and run my one variable statistics, you'll see that we have these two things pop up. We have S of x and we have our standard deviation. We have our sample standard deviation and our true standard deviation. These numbers are different. Now we are going to use S to estimate because this is a way for us to do a point estimate, even though these two numbers are different. So if we were to try to measure the variability here, we are going to use our sample because this is a sample again. So we are using S, and S was like 9.14 minutes. So this is a concept that you'll be asked about, and we'll further talk about it in class, but just these two numbers are fundamentally different, right? That's what a biased statistic is, right? It's not the same as the true standard deviation, but because we're using a sample, that's what we use. Even though it's biased, we will use that instead in order to find, in order to estimate what our standard deviation is. So we're using S, which is sample standard deviation.